Welcome to Embedded Academy. In this tutorial, we will interface an RGB LED with the 8051 microcontroller using Embedded C. This is the exact hardware setup we will build. As the program runs, you can see the components smoothly cycling through red, green, and blue continuously. To construct this circuit, you need three physical components: an 8051 development board, a common cathode RGB LED, and three 330-ohm resistors. For the software logic, you will need a standard C compiler and an IDE environment. Gathering these exact physical and digital components up front ensures that the code we write will translate perfectly into a working circuit. Looking at this 3D schematic, you can see that an RGB LED actually contains three independent light-emitting diodes, a red, a green, and a blue, housed inside a single transparent lens. We wire these colors to specific pins: red to port 2 pin 0, green to port 2 pin 1, and blue to port 2 pin 2. Before connecting, place a 330-ohm resistor on each pathway to limit current. Finally, because it's a common cathode LED, connect the longest leg to the board's GND terminal. With the connections secured, our physical setup is complete. The C code we write next will act as digital switches, sending power down these specific pathways. Here in our Keil IDE workspace, we will construct the digital logic to control that hardware. First, we use the S-bit command to assign symbolic names. We declare red, green, and blue at the top. We map red to P2.0, green to P2.1, and blue to P2.2. Using readable words instead of raw pen numbers keeps code clean. This brief declaration acts as a translator, allowing our human-readable logic to dictate raw electrical outputs on the physical chip. As this CPU diagram shows, the 8051 executes instructions faster than the eye can track. To make color changes visible, we introduce a delay function. Two nested for loops force the processor to execute empty operations, consuming clock cycles to create a 1-second pause. If you omit this delay step, the processor toggles pins instantly, and your LED will display as a solid, blended blur of light. Utilizing mathematical loops gives us control over time within the hardware environment, slowing the sequence down to a legible speed. Inside the main function, we set up an infinite while loop. This ensures our color sequence runs continuously as long as the board receives power. To begin the cycle, we turn the red pin on by setting it to 1. We also set green and blue to 0 so they remain off, and call our delay function. Next, we turn the red pin off with a 0 and turn the green pin on with a 1. We keep blue at 0 and call the delay again. Finally, we set red and green to 0 and turn the blue pin on with a 1. A final delay leaves the blue light visible before the entire loop restarts. By rapidly executing simple binary instructions, 1 for on and 0 for off, we completely control the behavior of the hardware. Now, compile your written code, flash it onto the microcontroller chip, and press the physical power button on your board. Looking at this cycle tracking graphic, your sequence should match perfectly. The hardware should cycle from red to green to blue, with clear pauses in between. If the LED appears white or flickers rapidly, your loops are processing too fast. Return to your delay function and increase the maximum values of your variables. Once it runs successfully, challenge yourself to expand the sequence. Try setting both the red and green variables to 1 at the same time to create yellow. By combining active pins, you can mix entirely new colors. Congratulations! You have successfully interfaced an RGB LED with the 8051 microcontroller using Embedded C. Understanding how to dictate hardware output with software logic is your first step toward mastering embedded systems.